Alright, so this is active filter design, lecture 31. In the last class, we were discussing the noise performance of the differential pair. Alright. Okay. VCM plus VD and VCM minus VD are the differential inputs. It's understood that there's a whole gamut of circuits attempting to force the output common mode voltage to VCM ref. Okay. And we are interested in finding the noise performance of this fully differential structure. And we notice that as far as the differential equivalent circuit is concerned, all noise from 2I naught as well as any noise coming from the common mode feedback error amplifier gets completely rejected due to the differential nature of the circuit. If you look at only the output difference, noise on VCM-FB will cause both legs to jump up and down by the same amount. Similarly, noise on the tail current source will also cause the same excursions on the voltages at both the output nodes. Thereby, when you look at the difference between the two outputs, that noise is of no consequence. Is this clear? All right. So, if we therefore look at the differential half circuit, the source coupled node is a virtual ground. Okay. This is VD. All right. And if you look at the noise current, there is a noise source in parallel with each transistor, and therefore, and we also saw that SIN of F is nothing but 8 KT by 3 times GMN, where GMN stands for the transconductance of the NMOS transistor. In a similar fashion, the spectral density of the PMOS noise current source is 8 KT by 3 GMP. The amplitude of both the units of both these spectral densities are ampere square per hertz. Okay. Now, therefore, if we kind of look at this transconductor as a black box, we see that the output current consists of two components. One, which is the signal current comprising of GMN times VD, which is what we want, and there is a noise component, and this component is IP plus IN, correct, which means that the spectral density of the noise component is nothing but 8 KT by 3 into GMP plus GMN. All right. Okay. So, if one wants to produce a noise current out which is 8 KT, which has a strength of 8 KT by 3 times GMP plus GMN, what would be the strength of a noise source applied at the input of the transconductor, which has right. So, this has this would be, I mean, if we want to find the equivalent input referred noise source, which when applied at the input of an otherwise noiseless transconductor and gives the same noise to the output of the transconductor, then this must be must have a spectral density SV of N of F times GMN whole square, right. So, the spectral density of the equivalent input referred noise source voltage is 8 kT by 3 times what? 1 by GMN times 1 plus GMP by GMN. Okay? And when we were discussing noise transconductors, we said that we can always express noise as for some 4 kT eta times the transconductance. Okay. So what is the transconductance of the transconductor? It's only GMN. Okay. And what is this equal to in this particular circuit? Eight kT by 3 times what is this? GMN plus GM. So the excess noise factor eta is nothing but 2/3 times 1 plus GMP by GMN. Okay. And we see that therefore that this 2 by 3 is coming because of what? That's coming simply because of MOSFET physics. It's got, there's no particular significance to this 2 by 3 other than that it comes from the detailed derivation of noise by when you know the physics of the MOSFET. So let's not worry about that. What we see is that there's another factor of the form 1 plus GMP by GMN. The intuition for this factor, right? You can see clearly that as GMP tends to 0 or GMN tends to infinity, we see that factor is 1. Okay. The intuition for this being greater than 1 is that this PMOS transistor, whose job in the real sense is just to provide that current which keeps the common mode voltage fixed. Correct? That's what the PNP transistor, the PMOS transistor is doing, right? But the fact that it is doing that also adds noise, right? But unfortunately, it's not adding any signal current. Whereas the NMOS transistor is adding both signal current as well as noise current. So if that's also evident in the expression for the input referred noise voltage, right? The NMOS transistor is adding a signal current which is GMN times VD and a noise current whose spectral density is 8 kT by 3 times GMN. So the input referred noise voltage there would simply correspond to 4 kT times 2/3 GMN. 2/3 times 1 by GMN. Okay. Alright. This extra factor 1 plus GMP by GMN is appearing because the total noise output current of the transconductor not only consists of the noise added by the NMOS transistor, but also that added by the PMOS transistor, which is not producing any signal current. So in principle, by choosing GMP appropriately, one can minimize the contribution of this so-called extraneous noise source, which is strictly not needed. Which can be strictly minimized, and reduced to 0, right? But that would mean, therefore, that the GMP would have to be 0, but which would in other words, GMP would have to be very, very small. Which means, what would you have to do in order to get? You still want the same quiescent current, but you want the GM to be very small. You would need a large overdrive. If you have a large overdrive, what would that do to the minimum supply required? If the overdrive of a transistor increases, you can say that the supply would have to increase in order to accommodate that overdrive, right? So you will see that with the finite supply, you cannot make GMP very small. Okay. In this respect, you are aided in fact by the fact that the mobility of the PMOS transistor is, for the same current, a PMOS transistor will have lesser transconductance than an NMOS transistor simply by virtue of mobility. So in that aspect, that's actually helping you here, right? But in general, we see that if you have very low voltage, then by definition, the amount of headroom you have to spare across, non-critical transistors like this one, which are there for bias purposes, is correspondingly reduced or increased. If you have a low supply voltage, the amount of the supply voltage you can, within quotes, waste on bias sources is also reduced, which means that if you do not want to make these, which basically means that the transconductances of all these transistors comprising of the bias sources will be, if you have a given current that a transistor needs to supply, and the amount of headroom you can afford is small, what does it mean for the transconductance? It means that the transconductance will increase. If the transconductance increases, what can you say about the noise? The noise also increases, and we have said by assumption that these are all transistors in the bias path, are not adding to the signal current. So these are will all contribute to this factor eta, which is the excess noise factor of the transconductor, right? Ideally, you would think that eta would be 2/3, because that's what MOSFET physics mandates, right? This extra factor of 1 plus GMP by GMN is coming because of this PMOS transistor, in this case, simply adding noise without adding any signal. You will come across this situation in several transistor circuit design, in several cases of, in almost all cases of circuits, where as the supply voltage reduces, the contribution of the noise from bias sources will start to increase, simply because you have very little headroom to spare across the bias devices, which will push up their transconductance, and therefore the noise they add. Okay, is this clear? Yes, sir, you're trying to ask me a question. Yeah. No. Pardon? Well, see, the question was, why are we even worried about signals when you're talking about noise? See, if a transistor produces a lot of signal current and produces noise current, it's okay. All right? I mean, that you can't help, because if you don't want noise current, you will not get any signal current, full stop. You understand? It's like talking to a person who, talking to a person who is generally talkative. Okay? Right? A guy who is generally talkative, A, can make sense, B, need not make any sense at all. Right? You understand? So, the NMOS transistors is like a talkative guy who also makes sense. Correct? So, you have to glean the signal from it and put up with whatever noise you get, because he is the only guy who can give you any information. You understand? Right? On the other hand, the PMOS transistor is a hanger on as far as the circuit is concerned, right? Who only talks nonsense, but he hangs around with this character, so there is really nothing you can do about it, right? So if you take these two as a pair, then the equivalent signal to noise ratio of the pair is degraded when compared to just that of the NMOS transistor. That's all, right? I agree completely that the PMOS transistor is, as far as signal is concerned, is completely redundant, right? But in the real circuit is definitely needed, because the PMOS transistor pushes down that current. I know. You understand? Again, I guess this is taking us out from this discussion, but it's a fairly straightforward thing to say. Hey, if these guys are causing trouble because they're only injecting noise current, why don't you make them inject signal current too? So in other words, do this. Okay, you understand? So here, closing your eyes, you can say that the excess noise factor will be, what is eta? 2/3, because the PMOS transistor is producing signal current as well as noise current. Okay, but you know, where do you think you will apply the common mode feedback? I mean, there are two ways of doing it. You can either make this current source dependent on this, or vice versa. Okay, and you know, we can go through the same arguments that we did and the same circuits and all that stuff. Okay. Anyway, it turns out this has got other problems, practical problems, but in principle, this is a transconductor with an excess noise factor of only 2/3. And this is a general principle in circuit design, right? There are devices in the signal path, okay, which do not push signal current, but only add noise, okay, then you're bound to, the excess noise factor is bound to increase on account of these devices. Okay. All right. Yes, sir. Yes. No. So please note, this is the differential half circuit. Okay. So far we have discussed the differential half circuit. We have seen already that if you take a differential system, then the SNR will be the SNR of the differential circuit will be what in relation to the SNR of the single-ended circuit? It will be 3 dB greater. So there is no point in sitting and drawing the entire circuit and complicating your life with twice the number of transistors and twice the number of noise sources, right? It simply suffices to draw the differential half circuit, right? Find the peak SNR and add 3 dB to the result. Does this make sense? Yes? Okay.
Sir,
yes. Yes. Right? No. See, I mean, there is no double counting here because there is VD on this side and minus VD on that side, and you know everything is okay. All right. So while we have done the noise calculation for one transconductor, the same procedure can be followed for any arbitrary transconductor, where the idea is one, draw the differential equivalent circuit, okay. Then then you can chop it off into half because of different symmetry and take only 1/2 of that differential equivalent, okay, and do the noise analysis for that. In this whole process, all the common mode noise sources will drop off, okay, or at least in any case it's very easy to recognize which of the noise sources are common mode in nature and get rid of them, and consider only noise sources which are differential in nature. The final SNR can be simply found by working completely with the single-ended schematic and then adding 3 dB to the final result. Is this clear? Okay. So that illustrates noise. The next thing is linearity, right? We have been kind of hand waving all along because we said that the linearity is a very strong function of the particulars of the circuit topology. So this is VCM plus VD, this is VCM minus VD. You understand? So let's call the overdrive of this transistor delta V1 and the overdrive of this transistor delta V2. So what is VGS of M1? VT plus delta V1, and VGS of M2 is Vt plus delta V2. What are we interested in finding? I mean, before we go berserk, we should be able to figure out what we are trying to find, isn't it? That we've assumed. I mean, so the first question is, are they in saturation? Yes, no, maybe. Yes, because all that stuff, common mode feedback, all that stuff is there, right? So that is not an issue. Okay, what next? What are we trying to find? What is the range of VD? That blah blah blah. What? Pardon? No. Just look at this diagram. What is the unknown? I say. Which I? Small I is all we're trying to find. From that, we can go and figure out all the other stuff that you guys are talking about. You understand? Okay. We are interested in finding out how that small I, right, is related to small Vd. Correct? Okay. So there you go through some algebra. It's not particularly inspiring, but we have to go through it anyway. So what is delta V1 minus delta V2? Delta V1 minus delta V2 is nothing but from these two, it's nothing but VGS of M1 minus VGS of M2. What is VGS of M1 minus VGS of M2? It's 2 VD, that's very good. Alright. And the sum of the two currents? Okay, anyway, so I naught plus I is 1/2 mu n C ox W by L times delta V1 square. Okay. I naught minus I is 1/2 mu n C ox W by L delta V2 square. Okay. Which means that half mu n C ox W by L times delta V1 square minus delta V2 square is 2i. Correct? So in other words, if we find delta V1 square minus delta V2 square, we are done. Yes? Okay. Now delta V1 square is nothing but what? This is nothing but delta V1 minus delta V2 times delta V1 plus delta V2. And what is delta V1 minus delta V2? 2 VD. Correct? Okay. So, and what can I cancel out? These two can go away. So, which means 1/2 mu n C ox W by L times VD times delta V1 plus delta V2 is I. Correct? All I have done is replace delta V1 square minus delta V2 square by 2 VD delta V1 plus delta V2. Is this clear? Okay. All right. Now, what about the sums of the currents of the two transistors? It's 2I naught. So, 1/2 mu n C ox W by L times delta V1 square plus delta V2 square is okay. All right. And so, what should we do now? You look at this character and say that delta V1 square plus delta V2 square minus 2 delta V1 delta V2 is nothing but 4 VD square. Correct? and delta 1 V1 square plus delta V2 square is nothing but two I naught into 2 by mu n C ox W by L, right, minus 2 delta V1 delta V2 is 4 Vd square. Okay. All right. So, which means what now? What is delta V1 plus delta V2? So, 2 I naught. So, 4 I naught divided by mu n C ox W by L is nothing but delta V1 square plus delta V2 square, right, plus 4 I naught minus 4 Vd square is nothing but delta V1 plus delta V2 the whole square. Does it make sense? This when expanded is delta V1 square plus delta V2 square plus 2 delta V1 delta V2. Delta V1 square plus delta V2 square is nothing but 4 I naught by mu n C ox W by L. The 2 delta V1 delta V2 has another 4 I naught divided by mu n C ox W by L. Add them together, you get 8 I naught by mu n C ox W by L minus 4 Vd square is delta V1 plus delta V2 the whole square. Does it make sense? Okay. So, delta V1 plus delta V2 is 2 times square root of 2 I naught divided by mu n C ox W by L minus Vd square, which means this times 2 minus Vd square is nothing but I. Okay. So, I therefore, the differential current on each leg is okay. I mean, this is only valid of course for VDs. I mean, only when the square root is positive, right? So, if VD becomes too high, then all those expressions don't make any sense, because all the current will go through one transistor, right? And the other transistor will have negative VGS and all that stuff, and in which case those equations don't make sense, correct? So, that's one thing to be aware of. The other thing is to get some, I mean, this looks like a messy expression, let's get some intuition on it. So, at VD is 0, In other words, for small Vd, what is I from the expression? Square root 2 I naught mu n Cox. Sorry. Okay, wait. Don't get too excited. Right? At Vd equal to 0, I will neglect this. Correct? And this will be square root, in which case this will be a constant. Then I multiply out the constant, the denominator cancels one factor, so you get this times Vd. Correct? Sure, at Vd equal to 0, I is 0, but around Vd equal to 0, what would you expect? The I to be linearly related to Vd, and sure enough it is. And what is that constant of proportionality? Gm of the transistor, which is carrying a current of I naught. Okay, this makes sense because this is what you would get from small signal analysis. But small signal analysis will tell you, if you extrapolate small signal analysis without thinking carefully, then you would conclude that regardless of how large a Vd I would put, I would get this Gm times Vd, which is not correct. The large signal expression here is telling you that as Vd starts to become large enough, the party is soon over, right? Because what happens? This factor goes on increasing or decreasing. As Vd increases, it will go, as the magnitude of Vd goes on increasing, this factor under the square root will soon eventually reach 0, correct? Which is telling you that whatever, right? The transconductance is whatever it is. All right. So another thing, please note another thing, that this comes from where? Where did that term come from? It's important to note that square root blah 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 is coming from delta V1 plus delta V2. Okay, so it is telling you that the sum of the overdrives, okay, is not a constant. All right, even though we can see that one overdrive is increasing and the other overdrive is okay. As Vd is increased, all right, what is happening to the overdrive of M1? Why? Okay, the claim is as Vd is increasing, the overdrive of M1 is increasing and the overdrive of M2 is decreasing. Why? The reason is the source is the same for both the transistors, right? So as Vd is increased, the gate potential of M1 is increasing, so clearly the overdrive of M1 is increasing and the overdrive of M2 is decreasing. However, it doesn't mean that the increase in the overdrive of M1 is the same as the decrease in the overdrive of M2. If that were the case, and let me repeat, it's not so. If that were the case, the sum of the overdrives would remain constant. But what is this telling us? The sum of the overdrives is actually, it is dependent on Vd, all right, but as Vd is increasing, is the sum of the overdrives increasing or decreasing? It is decreasing. You understand? Okay, and again, the sum of the overdrives is being constant is only valid at a pinch only when Vd is very, very small, in which case that Vd square can be neglected in relation to this voltage. You understand? Okay, so this is VCM plus Vd, right? This is VCM minus Vd, all right, and this voltage is what? VCM plus Vd minus Vt minus delta V1, and to make it a symmetric expression, what one can say is to say Vd is nothing but delta V1 minus delta V2. What is Vd in terms of delta V1 and delta V2? Half of delta V1 minus delta V2. So this is Vcm plus minus Vt minus delta V1, which is what? Vcm minus Vt minus delta V1 plus delta V2 by. Is this clear? Yes? No? Okay? Alright. And what is delta V1 plus delta V2? So this Vx, which is the tail source coupled node, is nothing but Vcm minus Vt minus 1/2 times 2, which is square root of 2 I naught by mu n C ox W by L minus Vd square. Correct? Yes. And does this make sense? When Vd is 0, what is Vx? Make sense? Yes, no? Come on, people. When Vd is 0, what is Vx? Yes, Suvinay? Minus square root of 2 I naught by mu n C ox W by L. So why does this make sense? I naught is flowing, so the overdrive of M1 when Vd is 0 must be square root of 2 I naught by blah blah blah. So it makes sense, right? Now as Vd is increased, right, as the differential voltage is increased in magnitude, what is happening at Vx? It is increasing or decreasing? It is increasing. Okay. Another thing which also makes sense, please note that Vx is symmetric with respect to both the input voltages. Therefore, it must be an even function of Vd. You understand? Alright? Vcm plus Vd is here and Vcm minus Vd is on this gate. This node is common to both sides, right? So if I make the left node Vcm minus Vd and the right one Vcm plus Vd, nothing really changes as far as Vx is concerned. So Vx must be an even function of Vd, which is also what you see makes sense. Correct? And quite interestingly, Vx goes up as Vd is increased, right? Okay, and you can see that the this node Vx being an even function of Vd, right? If you expand an even function as a Taylor series, what is the first term you will get apart from the constant? You get a square term, correct? So and Vd square, I mean, so if you expand this weird looking expression out as a Taylor series, apart from the constant, you will get a square term, right? And squaring, a differential voltage, correct? To get something which is proportional to the square of the input differential voltage, which is needed in several applications, one often taps off the source coupled node. You understand? By exploiting the property of the differential pair, that this node for large Vd, right, will have a potential which has got a square term, which means that it can be used to sense the square of the input differential voltage, and that's got some applications. You understand? Okay, so if you plot it, if you plot Vx as a function of Vd, how do you think it will look like? How does it look like? It's an even function, so without thinking too much, it must look something like that. Okay, so which means that if you want to measure the amplitude of a sinusoid, for example, right? I mean, should it go? Sorry, this is fine. Okay. Oh, sorry, it is plus. Sorry. Yes. Okay. So, so if you are interested in finding the square value of the input differential voltage, one can simply monitor the average potential at the potential at Vx, and that's an indication of it's got a quantity which is dependent on Vd square. Okay, so you can see that the differential pair is really a very versatile circuit, right? There's all sorts of, depending on where you look, there's all sorts of information in. Okay, all right. Anyway, so what is the maximum Vd I can give before all the current is switched to one side? Okay, so in other words, if I plot I versus Vd, the slope is known from the small signal transconductance. What is the maximum value of I? Now, the maximum value of I, small I, please. The small I is the difference between the drain current and I naught. I naught. Maximum current is I naught. Okay, understand? And in fact, it's not something which would go asymptotically like this. Beyond a certain point, it would just flatly go to flatly saturate. Okay, and you can go and find what if delta V is denoted as square root of 2 I naught by mu n C ox W by L. This will be nothing but root 2 delta V. Correct? Because if you need the current, originally when the Vd was 0, the current flowing per leg was I naught. If you want the current to double, in other words, if you want to find when the current becomes 2 I naught, which is equivalent to saying small I becomes equal to I naught, then the overdrive must go up by a factor of root 2. Simple as that. Okay. All right. Understand? Another thing I wish to point out is that the differential current, okay, this I, or do you think it's an even function of Vd or an odd function of Vd? It's an odd function of Vd. And why does that make sense? Yeah, so you have two circuits being operated in what you call anti-parallel fashion, right? So, and if each circuit is nonlinear, let us say it produces harmonics, right? Second, third, fourth, and so on. right? When you find the difference between one being operated with Vd and the other one being operated with minus Vd, all the even harmonics will cancel, only the odd harmonics remain, and this is an attribute of all differential circuits, correct? Even if they're, if they're nonlinear, you understand? If they're linear, then there's no question of harmonics at all. If you have two nonlinear circuits and operate them in a differential fashion, then if you look at the difference between two node voltages, which is what your output quantity is, then all even harmonics go away, right? This is one more advantage of differential operation. Is this clear? Okay. Yes, a common mode will have even harmonics. And when there is mismatch between the two halves, what do you think will happen? The cancellation of even harmonics is not exact, right, or not perfect, and but you live with it. It's certainly better than having, cancelling off 90% of the second harmonic is certainly better than not cancelling off 90% of the second harmonic. That's all, right? So you can't be better off, you can't be worse off than the basic circuit itself. All right. So given that this S-shaped nature of the I to V characteristic, we can all come to some agreement on what we say constitutes the linear range. This definition is as open to interpretation as anything else. One might say, okay, I will plot the transconductance as a function of Vd, right? If I plot the transconductance of the transconductor, in other words, if I plot the slope of this curve or this characteristic, what do you think it will do? It will be maximum where? At the origin and kind of fall off towards 0. It will go to 0 at root 2 delta V, right? So you can go fight it out and then find the point at which, say, the transconductance drops off from its maximum to, say, 90% or 80% or 50% of its maximum value, and call that the linear range. As long as you're consistent when making comparisons across different transconductors, any different definition is valid. You understand? So some of you might say, hey, what is so sacred about 10%? I want to use 20%. Yeah, sure enough, use 20% for every transconductor that you wish to compare. You understand? Okay. All right. So this kind of analysis, in other words, this large signal analysis, or in other words, what happens to the output current when the input differential voltage is large, can be done for any transconductor. You understand? Okay. All right. And therefore, so all these calculations of linear range and all this stuff will depend on the specific transconductor that one is actually working with at that particular point in time. So let's look at other transconductors and see if we can do better than the differential pair. Since we are at it, we might as well also wind up on the differential pair, talking about some of its good things and bad things, right? So let's begin with the good stuff first. What is the input impedance of the differential pair? Well, if you're only interested in differential inputs, okay, what is the input impedance? What is the equivalent circuit of the MOS transistor of high frequencies? It simply looks like, I mean, the source coupled node is ground anyway. So the input impedance is 2/3 Cox into W into L. Okay. So is this a good thing or a bad thing? Not a good thing. Why is it not a good thing? Okay. So one say, okay, you would like to have zero input capacitance, but it's impossible to have. I mean, finally, if you want transistor action, then you need the gate capacitance is an integral part of the whole how the transistor operates. So if you have no gate capacitance, you have no transistor, right? So I mean, so you can't avoid the gate capacitance. Okay, but you could have been doing lot worse. Why? I mean, the input impedance was resistive, then you are screwed, right? Why? Because this is going to come in parallel with. Please note that this transconductor is sensing the voltage across some capacitor and so on, correct? When you make the integrator. Now, if this input impedance has got a resistive component, then it's going to reduce the Q of the biquad that of the biquad. So that's no good, right? So in that sense, we are in fact lucky that the input impedance is purely capacitive, because this capacitance can be thought of as being part of the integrating capacitance, right? You understand? Of course, we'd love it if the input capacitance was 0, but then you won't have the transconductance will also be 0. You understand? So that's not an option, correct? Why I am insisting on this, or rather emphasizing this, is that when we go further, you will see, we have all sorts of transconductors where the DC input impedance is high, sure enough, but as frequency increases, the input impedance is not as clean as a capacitor. It's got inductive components and negative resistive components and so on, which kind of becomes sometimes problematic, which is why I'm bringing this to your attention. The other thing is the finite output resistance of the device. Okay. So what will be the DC gain of the transconductor? The DC gain will be GMN times please note that the differential equivalent, there is another PMOS transistor at the top. This chap is adding noise, is not adding signal, and also contributing to the output impedance and parasitic capacitance, because the PMOS transistor will also have a parasitic capacitance from the drain to the substrate. Okay, so this is the DC gain, correct? Please note that every transistor will also have parasitic capacitance. I mean, so this is CGS, this is CDB. This CDB will consist of the CDB of the NMOS transistor plus that of the PMOS transistor. And again, you may say, oh, well, I'd like to have a transistor without CDB, but you cannot. You can only have something with a small CDB. It's not fundamental to the operation of the device, right? But at least it's a capacitor, and you can kind of account for it in the integrating capacitors, right? Now, if you keep saying, now you say, oh, you take every capacitor and keep accounting it for the integrating capacitor, then what if you have no integrating capacitor left? You understand? That means that means the frequency at which you're designing is so high that you can no longer do it in this technology. You've got to go to a better CMOS technology where the parasitics are lower. That's all it means. You understand? I mean, if you have a given technology, there's only so much you can do. Okay. All right. Yes. 2/3, no? This is the half circuit, right? So if you look differentially, it will be 2/3 Cox WL in series with 2/3 Cox WL. Just like how the integrating capacitance was put to ground. In principle, you could have made it 1/2 the capacitance floating between these two nodes. Okay. All right. Now the next thing. All right. Another thing I'd like to point out. And when people keep drawing gyrators and so on, they will always draw the single-ended equivalent because the differential equivalent is just extremely confusing without adding any new intuition, right? So when people say, okay, this is the equivalent, this is the circuit diagram of the gyrator, right? Even though they draw a single-ended equivalent, what it means is that in principle everything is fully differential. Just to avoid clutter in the diagrams, you always show the single-ended equivalent. So this is Gm, this is minus Gm. This is C. All right. So can you comment on the common mode, the input and output common modes of the transconductor? In other words, we have said that the fully differential transconductor is associated with an input common mode voltage VCM and an output common mode voltage, right, which is forced to VCM ref by a common mode feedback loop. Now the question we am asking is, does it make sense to keep VCM different from VCM ref? In other words, the input common mode voltage and the output common mode voltage, do you think they can be different? They cannot be different? I mean, ideally it would make, I would think that, I would always like to retain the freedom of making the input and output common mode voltages different. I mean, okay, if I want to make them the same, it's very easy, right? But the question is it possible to have that luxury in the context of a filter where transconductors are connected in this fashion? Yes, no? That's all okay. But look at this circuit diagram. Yeah, okay. So what? Yes. Yes, so what is the bottom line? So this is going to be, if you want to have the same transconductors used everywhere, right, then this common mode voltage here will be VCM ref. Why? It's being forced by the common mode feedback loop of the transconductor on the top, right? What is the common mode voltage here? VCM ref, because it's being forced by yes. So then the next argument is, hey, why don't you use two types of transconductors, right? Where the input common mode range of 1 is higher than the input common, than the output common mode range. The input common mode voltage is higher than the output common mode voltage, and use another kind of transconductor where the reverse is true. Then you can put them in a loop and both will be happy. You understand? It's generally a mess to do. Right now you keep track, unless there's some very specific reason to do so. There's usually, it just makes life more miserable than it already is, and then you don't need no more miseries. You understand? So a common practice is to simply keep the output common mode the same as the input common mode. Okay. Right. So now our modified fully differential transconductor looks like okay, and the output OP and OM is maintained at VCM also, correct? And under these circumstances, we got to make sure that all the transistors still remain in saturation. Is that true or not? Yes, no? If VD is 0, for example, this voltage, this potential are the same. So the transistors are in saturation. And the PMOS transistors, of course, are coming. I mean, it's as far as the PMOS transistors are concerned, it's straightforward to keep them in saturation, simply because their drains are at VCM, the sources are at VDD. So as long as VDD minus VCM is much larger than the overdrive of the PMOS transistors, it's actually quite straightforward, right? And again, I'd like to remind you that it's not particularly a great idea to choose. I mean, if we use the kind of common mode feedback loop that we discussed, right? We have a two-stage op amp as the equivalent for the common mode feedback loop. We see that it is not particularly a great idea to have choose a GMP which is very small. Choosing GMP to be small is advantageous from one point of view. What is that? Noise wise, it makes the excess noise factor of the transconductor smaller. But why is this? Why is it also a damaging thing to do? The common mode gain will increase. Okay, if the common mode gain increases, then if you put the transconductor as a gyrator, then we saw that there is positive feedback and the tendency to oscillate will increase, right? So what I would do would be to choose GMP to be not too small so as to cause common mode instability when you make the gyrator, and not too large, okay, so that the noise performance is compromised. I mean, like everything in engineering, it's a trade-off. Yes?
So, when VD is not 0, then my drain voltage will depend on the integrating capacitor.
Yes.
So, it should still remain in.
Yes. It goes without saying that the voltage, I mean, the transistor must remain in saturation for the entire range of operating voltages. We know that also we know that this I mean the dynamic range of the filter has been already scaled, correct? So we know that the peak swings at every capacitor node is the same, correct? So in the absolute worst case, if this is VD max, the drain can go down only by VD max. You understand? Is this clear? If VD goes, I mean, if we this increase, what Suvina is saying is that, hey, it's not just enough if when VD is 0, the transistors are in saturation. We need to obviously make sure that this is true for all values of VD which are within the linear range of the transconductor, because we will be operating, as we discussed, with as large a signal as possible without compromising linearity, right? So if we all decide that VD max is the maximum value VD can be, then by virtue of dynamic range scaling of the filter, the drain swing can also not exceed VD max, right? Which means that the drain in the worst case, right, can go how much below the gate? Okay, the drain can go at the most 1 VT below the gate, but if VD max is the swing at the gate and the drain, what's the worst case? The gate can go 1 VD max above VCM and the drain can go 1 VD max below VCM, correct? So the worst case is 2 VD, absolutely worst case, okay? In practice, of course, in the filter it may not be such that the phase difference between the drain and the gate need not be 180 degrees. right? It depends on which node in the filter you're looking at. Okay. So so the absolute worst case must be that Vd must be chosen to be less than. So Vd must be chosen to be less than or equal to Vt by. Correct? With the VTs of 0.6, 0.7 volts, that kind of thing, Vd will be 300 millivolts, that range. Okay, 300, 350 millivolts. Okay. And you will know that, to get sufficient linearity at 300 millivolts itself will be a challenge. So most often you will find that this is not too difficult a constraint to satisfy. Okay. Does it make sense? All right. And this is somewhat of a pessimistic limit also, because you are expecting the drain and the gate to be 180 degrees out of phase, which usually doesn't happen at all nodes. Okay. Now the next thing I'd like to point out is that, so the good things about the differential pair are capacitive input impedance, right? And if you think about it, the number of signal nodes, the number of extra signal nodes other than those carrying the input and output voltages and currents is, see, you have a black box. Its input nodes are the two input voltages which come in, the output nodes are the two currents which go up, right? Okay. You understand? So what is the bare number of nodes required in the circuit? You at least need 4 signal carrying nodes in a fully differential transconductor, full stop. Correct? Of course, you could have a lot more. You understand? Right? But if you have a lot more, what do you think? What kind of problems do you think you might run into? If there are more signal carrying nodes in the network than necessary, every node is associated with a parasitic capacitance, which means some of the signal current will be lost through those parasitics, which means that weird stuff can happen. Right? So the best case is when you have exactly the minimum number of signal carrying nodes. And the differential pair, one of the big advantages of that is that there are no, if you look at the small signal equivalent, the signal carrying nodes are just the minimum required, right? The gate of the transistor, the drain of the transistor, full stop, nothing else. Okay. On the other hand, the bad things about the transconductor are, and nonlinearity is a very generic term. Any circuit made with transistors will be nonlinear eventually, right? So you will find as we go along, we will find that there are other circuits which can be a lot more linear than the differential pair. And more importantly, if I want to double the linear range, what should I do to the current? Double the linear range by whatever metric. The linear range must be a function of delta V. Okay. So if I want to double the linear range, I must double delta V, right? Which means that the what do you call, if I not really 4 times, right? So if I twice the linearity means twice the delta V, correct? But I want the transconductance to be the same. So what must happen to the current? In both cases, 2I1 by delta V1 must be the same as 2I2 by delta V2, If delta V2 has to increase by a factor of 2, what must happen to I2? Must also increase by a factor of 2. I mean, if I simply increase the delta V by a factor of 2 and do nothing else, what will happen to the current will go up by a factor of 4, right? And transconductance also go up. To make a comparison, you must compare with, you can't compare apples and oranges, right? So you must make a clean apple to apple comparison. So the first thing at least is when you compare to transconductors, their transconductances must be the same when the signal is small. You understand? And also the DC gain of the transconductor is what now? Can you comment on it? In respect to the GMRO of a transistor. It's roughly of the order of GMRO by 2, where GMRO is the gain of a transistor. Correct? So the DC gain is low. Pardon? I mean, is of the order of GMRO by 2. It is GMN times RON parallel ROP, right? So unless we know RON and ROP, you can't make a value judgment. It must be of the order of 1/2. If your RON is the same as ROP, it's 1/2, right? It will be around about there. Okay. Again, we see that the PMOS transistors, which are supposed to act like current sources, simply not only add noise, they also degrade the DC gain. So what do you think we can do to fix the problem? What will I do to pardon? Okay, the easiest thing to do is to cascode the PMOS current sources. Okay. So how many of you have seen this arrangement of transistors before? All the MS and MTech and all these guys must have seen it. What about the BTech students? This was there in your tutorials. Yes, do you recognize it? Yes, no? No? Okay. Alright, let me explain quickly what this is. Okay, let's say this is connected to some bias voltage. I'll do everything with NMOS transistors because you're more familiar with them. The same logic can be extended to PMOS designs. Okay. All right. You understand? Now, what is the output impedance, incremental output impedance looking in here? RON, I'll just call it RO just to prevent carrying subscripts. Okay. Now, if I want to increase, in other words, this is not as great a current source as I want, let's say, because of the finite RO. What is the meaning of finite RO? Ideally, if this was a perfect current source, then regardless of the voltage, I mean infinite output impedance. Yes, what does that mean in English? Regardless of the voltage across the current source, the current it sinks will be absolutely the same. That's what it means, right? Unfortunately, that's no longer true with a current source with a finite output resistance. Okay, so if you want to take a non-ideal current source, in other words, a current source whose output impedance, incremental output impedance is not infinite, okay, all right, and make it look like a better current source. In other words, make it look like a current source with a, what is a better current source? Higher output impedance. Then what would I, what would I put between, if there was a contraption, if there was a black box here, right? What kind of control source would I put? I mean, clearly this has to be a controlled source because its output depends on, this output is a current, correct? It depends on the input current, so it better be a controlled source. Now, what kind of controlled source would that be? This must be a current controlled current source. Okay. All right. All right. Now, so what is the simplest current controlled current source? Common gate amplifier. So, all right. This is the CCCS. All right. When is the common gate amplifier, or when does the transistor behave like a current controlled current source? Under what conditions? It must operate in saturation. Okay. So, let's say I'm going to redraw the same thing. This is the current controlled current source, the device on top. It must operate in saturation. Let's say I bias the gate at VB. What is the lowest voltage this can go to? Let's assume that all the transistors are equal in size. What is the lowest this D can go to before the transistor goes into the triode region? VB minus. So, let me call this D. VD minimum is VB minus VT, right? And VD minimum is the minimum drain voltage required in order to keep this guy M2 in saturation, correct? Now, what is the potential at the source of M2? VD of M1 is nothing but VB minus VT minus delta V. Let's assume all the transistors are the same, have the same overdrive, correct? You understand? Okay. All right. So, but if you want M1 to be a current source, M1 must be what? Come on, people. In saturation itself, which means that this must be greater than, the drain of M1 must be greater than, what is this potential? VT plus delta V. All right. So, what is the minimum voltage at the drain of M1? This must be greater than delta V, which means VB must be greater than, come on people, VT plus 2 delta, correct? Okay. if Vb is chosen to be its minimum of Vt plus 2 delta V, what is Vd minimum? 2 delta V. Okay. So what is the moral of the story? Assuming that this current controlled current source trick works, we have paid for it in terms of the minimum voltage required across this current source in order for it to behave like a current source. Earlier, if only M1 was there, what was the minimum voltage required across it? It was only delta V. Now it is 2 delta V. Okay, so that's what we have paid. Now let's see what we get in return. What are we expecting? What is output impedance here? RO. So what are we expecting now? If we operate both the transistors in saturation, what are we expecting? We are expecting this output impedance here to be much higher than RO. Yes? Both the transistors will have the same RO. Right? Right. But that doesn't mean the output impedance looking in here. We are looking at the incremental impedance from here to when we say RO, we are looking at the impedance between that node and ground. Yes? Is this clear, people? Alright, how do you find the output impedance now? Yes, the BTEX, come on. Chinnadurai. Incremental equivalent circuit, what might that be? What is the incremental equivalent of the lower transistor? What happens to VB1 and VB2? VB1 is grounded. VB2 is grounded. What about VB1? Dinesh Jayaraman. VB1 is also grounded. Great. Okay, what happens to M1 then? Yes. So what will happen to V1, to M1, the lower transistor? Resistor. Okay. So let me call that X. So from X to ground there will be a resistor. Okay. And what is the value of the strength of this current source? GM into gate voltage is 0 minus incremental voltage here. Correct? Does it make sense? Okay. So I can replace it by a current source GMVX. Correct? To find the output impedance, what would I do? I would pump a current and measure the voltage. Why does that make sense? Stuff is in series. Okay. So if this is I, alright, what is Vx? Vx is nothing but I times R naught. Correct? So this current is nothing but Gm times Vx, which is Gm R naught times I plus I plus plus R naught into I. I'm so sorry. Yes, it's Gm R naught into I plus I into R naught is the potential drop across R naught on the top, plus I R naught is the potential drop below. This must be equal to VO, which means that the output resistance is pardon Gm RO into RO plus which is approximately okay. So have things improved or things become worse? Improved, because earlier the output impedance was RO and now it is GM RO times RO, right? So it's an order of magnitude improvement in the output resistance. Yes? Okay, fine. All the math is fine. Let's get some intuition quickly on why this result makes sense. Let's say you have a transistor like this. Let's say it's carrying a current I. All right. This transistor has got a transconductance of Gm and an output impedance of R naught. It is sitting in the saturation region, which means that the drain potential under quiescent circumstances is sufficiently high compared to the gate. All right. So now, if this potential, let's say this was this, okay, and this will be Vs. Now, if this increased by a small amount and this increased by another small amount, then what do you think will happen to the source? It will be increased by some amount, we don't know what, we'll figure it out. Okay, only thing I need to know is that it changes, right? Now, if it doesn't change, then I'll have to explain why it doesn't change, but if I assume that it changes, it's perfectly okay, right? Now, I'd like to figure out how the source potential changes in response to changes in the potential at the gate and the drain. So, originally I was a function of VGS and VDS. Okay. All right. Now, delta I, which is the change which would in the drain current due to a change in the gate source and drain source voltages, must be of the form Gm times delta VGS plus GDS, or which is 1 by RO times delta VDS. Correct? In general, if I took a transistor and change its gate source voltage and change its drain source voltage, this is the change in the drain current due to the change in the gate source voltage and the change in the drain source voltage. Yes? No? Come on. Okay, what is delta I in this particular example? 0. Why? The current source, so this must be 0. Correct? So what does this mean? 0 is Gm times Vg minus Vs plus 1 by Rho into Vd minus Vs. This is Gm times Vg plus Gm plus 1 by Rho times Vd must be equal to Vs into Gm plus 1 by Rho. Okay. All right. So, in our example, Vg is 0 because or rather, if Vg is 0, in other words, the gate is not yanked, it's only the drain which is yanked. Okay. If Vg is 0, then and only Vd was yanked up. Vd is nothing but Vs times Gm Rho plus 1. In other words, Vs is Vd divided by you understand? Okay. So the intuition behind this equation is, all that it's saying is that this equation is telling you that the change, if the transistor is operating in the saturation region, then a change in the gate source voltage will cause a large change in the drain current when compared to the same magnitude of change in the drain source voltage. Correct? In other words, in saturation, GM Rho is a very large number. Correct? So, what is this telling you? This is telling you that if the gate source voltage and the drain source voltage change by the same amounts, then the change in the drain current attributable to the gate source voltage is much higher than the change in the drain current attributable to the drain source voltage. In other words, the gate has a lot more influence on the drain current than the drain. That's all this is saying, right? In our particular example, since we have a current source, if I yank the gate and the drain, then delta I is 0. So, if the gate goes up by some amount, since the effect of the gate source voltage is much larger than the effect of drain source voltage, right? What do you think the relative changes due to the gate source and the drain? Can you comment on the relative change in the source voltage due to a change in gate versus due to a change in the drain? The gate will be much more, right? In other words, the change at the source due to a change in the gate will be much more than the change in the gate due to a change in the drain. Change in the source due to a change in the drain. Okay. So, for example, the equation also is telling you this. Okay. Vs is Vd divided by 1 plus Gm Rho. The Gm 1 can be discounted in relation to Gm Rho. So, Vs is Vd by Gm Rho. Okay. On the other hand, what is Vs in relation to Vg if Vd is 0? All that we have to do is replace Vd by R naught with Gm Vg. In other words, replace Vd with Gm Rho times Vg. Yes, no, come on people. Yes, Palni Rakesh. It is Gm R naught by not by 1 plus Gm R naught. And this makes sense, right? It's telling you that if the source current is constant, then if the gate goes up by some amount, source will go out virtually by the same amount, right? By why virtually the same? Okay, so I mean if R naught tends to infinity, clearly Gm R naught tends to 1. So if the gate goes up by some amount, the source must go up by exactly the same amount. Otherwise the current will change, which is a contradiction. So in other words, if I took, so the bottom line is, if I took a transistor, had a current source here, if this was connected to a constant potential VB2, and if I yank this by delta V, how much will this go up by? Approximately delta V by GMR. Correct? Now, instead of having a current source, if there was something whose incremental resistance was R, right? How much current will flow? Voltage divided, the change in the current will be delta by R. By R. Correct? So where is that current flowing? Like this. So what is the output impedance? Is GMRO times you understand? So in other words, the output impedance is enhanced by a factor GMRO. In our case, we have a special case where this R also happens to be R naught. You understand? So the output impedance approximately becomes GMRO square. You understand? Okay. You understand? Okay, so this is the intuition behind why a cascode helps increase the output impedance, because this voltage can be varying wildly, but the voltage at the source will be, the variations will be attenuated by approximately GMRO. Correct? So whatever you had before, you had the lousy current source before, it is seeing only a much smaller variation, which means that effectively its output impedance is getting multiplied by GMRO. Does it make sense? In fact, all this stuff was there in one of the EC201 tutorials, which of course none of you have done. So, all right. Understand? So whatever I have discussed for NMOS transistors also hold for PMOS devices. So to simply, to fix the problem that the output impedance was unnecessarily getting reduced by these PMOS devices, which are not doing any particular thing as far as the signal is concerned. They're pretty much you're doing just bias work. So and they're also screwing up the output impedance. So to fix that, we can enhance the output impedance of the PMOS devices by putting devices in cascode. You understand? Okay. So, what is the, if the overdrives, if both the devices are identical and the overdrives are delta V, what is this potential? VDD minus delta V minus VTP mod VTP. Okay. What is the lowest this voltage can be? I mean, if you want this transistor to be comfortably in saturation, do you want this potential to be very low or very high? You want it to be as low as possible, correct? But so in other words, how high can it be while still ensuring that the top PMOS transistors are in saturation? And what happens as this potential keeps going higher and higher and higher? Source will keep going up. Sure, what will happen eventually? The top transistors will get into triode region. So there's a value beyond which the gates of the cascode devices cannot be increased. And what is that value? In other words, what is the value, what is the highest value of VB2 that one can use while still maintaining both the transistors in saturation? Pardon? VDD minus 2 delta V minus VT. Very good. Okay. Of course, like all engineering situations, it's not good to operate on the edge. You will always have some margin. Okay. All right. So now, if you do this and add common mode feedback, all right, then you have a transconductor where the output, the gain, DC gain is GMN times RON. Okay, and because the output impedance of the top PMOS current sources, which was originally ROP, has now become GM-ROP times ROP, which is an order of magnitude larger than what it was before. So one can conclude safely that you're pretty much being, the DC gain is being limited by the output impedance of the NMOS transistors. So the DC gain will approximately be GMN times RO. Okay, so now once we find that the cascoding trick works, right, it's natural to become greedy and say, hey, why don't we? Sure enough, let's try. Okay, so let's see what happens when. So any comments on this? To increase VDD to support? Okay, fine, all right. What else? Is there a more fundamental thing? So what can you say about the input and output common modes of the transconductor? In the gyrator, when we put the transconductors as a gyrator, what did we say? The input and output common mode must be the same, right? So do you think this is more difficult to do or easier to do? I mean, the cascode only helps if all the transistors are in saturation. You understand? Now what happens? earlier, delta V, I mean, how low could this go? So, you had one transistor, so whatever, Vt by 2 was the maximum each node could swing. Now, what happens? You have two transistors. So you lost some of that swing already because of the extra cascode. Okay. So, it's kind of hard to fit. You can at a pinch fit two cascodes, but then you will find that the amount of headroom you have left for the signal swing has all been eaten away by the cascode. The next thing is that now you have two new nodes in the signal picture. Correct? Yes, no? Right. So, the parasitic capacitance of these nodes will add extra poles, which means, the GM is not really a GM, but some GM divided by 1 plus some S by omega P1, where P1 corresponds to the pole at this node. So, because of this double whammy, right, you get higher output impedance, but the signal swing possible is reduced. So, this is not a particularly a smart thing to do, because the signal swing has come down considerably. Yeah. All right. So, I mean, see, one more thing that we should generally be wary of in analog design is when you seem to be getting something for nothing, always there is likely to be a catch, right? So, here we seem to be increasing the output impedance, but you added one more device which also adds noise. So, there are three possibilities. The extra noise, I mean, is very small compared to what was already coming out, in which case we are happy, right? The extra noise is equal to the noise which is already coming out, in which case it's bad, right? The extra noise is much larger than the noise which is already coming out, in which case it's very bad. Okay. So, before we jump to conclusions, start putting cascodes all over the place, one thing we ought to do is to see what effect the noise of the cascode has on the okay. So, I think I see everybody is very sleepy. I will stop now and continue.